Hey guys, thank you for watching part one of this series. I would just like to apologize that the first 15 or 16 minutes of this video, for some reason, the audio on my laptop got a bit echoey and robotic. So please bear with the audio. It improves after the 16-minute mark. Thank you for also clicking on this video, and I hope you guys enjoy this series. Thanks. Okay, welcome everyone to the part one of the series where I go through this website, which is called Roadmap.sh, and it's basically a roadmap on like everything that you need to know in order to be a developer or to get a computer science job. I think they do a pretty good job on picking like the topics that you need to use in order to guide your learning. I'm just going to go over what my take is on this whole blueprint, I guess, for getting a tech job. This is also going to be like my take on it, and I'm not going to teach you everything that's on this website. It's impossible to know everything. So I hope by going through this tutorial, I can maybe steer you more so in the direction of things that I think that you should know. And then I know there's definitely people out there who would disagree with me. And if you do disagree, make a video and we can compare approaches. Just to give you guys some context, I do have my PhD in computer science. I graduated in 2024 in December, but I stuck around with my advisor and I had to be enrolled as a student at the time. So I ended up graduating in May 2025, and I found a job in tech working for a startup as an AI engineer. So I'm an AI engineer at a startup working part-time, and I'm also a research AI engineer working with the university. Okay, so let's get started with this tutorial. So right off the bat, they say to pick a language. Of course, whenever you're trying to learn about computer science, the first thing that you're going to be doing is learning how to code. And they give you a few choices here on programming languages that they think is important. I'd say Python is one of the most popular programming languages that I think you should learn. Everyone wants to get an AI tech job. Python is this high-level language that has libraries that allow you to use a lot of the AI functionalities. That's not to say you can't do AI with these other programming languages, but Python would be one of the most supported languages to create AI applications. And you can also use Python for building web applications, but JavaScript is also a pretty popular language. If you want to become a web engineer, then you probably need to know JavaScript and of course HTML and CSS. Nowadays, a lot of people are using Wix, WordPress, Shopify, and in those applications, you have this GUI where you can just drag and drop elements onto the website and build it that way. They have within those web designing builders a section where you can implement your own custom code. I believe you can input some JavaScript in there or some HTML. But yeah, I think most of the time, if you were to go find a job, they might even tell you to just use the GUI that they have. It's not until you work for maybe like bigger companies, like Fortune 500 companies, or especially companies in big tech, they'll probably want you to more so to use programming. And in those cases, they're mostly dealing with JavaScript and Python anyway. Those would probably be my top two on what I think that you should learn. I also met recently with GitHub, and there's these other languages here, Go and Rust. So they said, or they recommend that a lot of the development that they're doing, they're moving more towards using Rust and Go. And I think there's some other YouTubers on here. I think Tech with Tim, if you guys ever watched him, he also goes over Rust, and I think he has a good tutorial on it describing like what it is, what it's used for, how it's optimal for some use cases, and what you shouldn't use it for. So these languages, it's good to pick one to learn all the fundamentals on, but basically you pick a programming language for the use case. If I were to do low-level programming where I need to have access to the hardware components of the computer and I want it to go very fast, I'd probably use something like C and C++, because when I say low level, it gives you the lowest access to tell your computer on what to do. For example, Python is built off of C and C++. When you call a function in Python, it's actually running C code underneath it. So Python is like a higher abstraction of running a bunch of different C code. And then C is one level lower than that, will probably be assembly language. So C is actually running like a bunch of assembly code, and assembly language is running a bunch of binary code. If you want something to go very fast, or if you know exactly what you want the computer to do, you might run it in binary code. I don't know if you can program in binary. I guess you can, but what I'm trying to say is that if you want to learn more about computer science and do something that's applicable, you'd probably want to pick a language that the job requires. Another way of doing that is just to go on LinkedIn, search up the kind of jobs that you want, and then you'll see the frameworks of what they're looking for. Maybe they're looking for JavaScript and React framework. Maybe they're looking for Angular. These are like the kinds of keywords that you need to use to guide your learning to target the job that you want. Okay, I hope that makes sense. This also says C and C+. Start off with that, but I disagree. You just pick a language that you want to get a job in. Data structures. So data structures are basically ways that you would structure your data in order for you to use it easier. For example, an array, I should have had some, let me see, can I go, try to draw something out for you guys real quick. Okay, so we're gonna do like Python code in here. So zoom in here. And so this is what a array looks like, and these quotation marks, it's called strings. So it's a collection of characters. We'll write Honda here, we'll write Toyota, we'll write Ford, and then we'll do, sorry, you capitalize these, and then we'll do Mercedes. Okay. So this is an array. This is a collection of strings. Alternatively, the way that you would write this as not representing an array, you probably do a Honda name, Honda, and then you would have a bunch of variables here, and then so on. The reason why this is useful is because if I wanted to maybe update the letters, the first letter of these car brand names, I will need to do Honda name. You would do something like this, right? So if I wanted to capitalize this letter here, I would grab this variable, Honda name. I would grab the first index, which is the H, and I would assign it a capital H. And then I would need to do it for the next variable, which is very time consuming. And if you have 50 car brands here, it'll take you a long time to write all of these out. Instead, what these data structures allow you to do is that you can do for name in car brands. This is also in Python, and then you would have an index. You can add a tab there. Name, how would I do this? Name.0 equals name 0 to uppercase or upper. I think that's how you do it. So if you had 50 car brands in here, you can just write 2 lines of code, and then you can run logic on every single string within this array instead of doing it all one by one. You need to do Toyota, Ford, Mercedes, Mustang. Well, Mustang's a make, but yeah, you get the idea. And another thing that these arrays have that's built into it is functionalities. So you have this list here, right? And say you're showing this list on a website, and your boss comes up to you, he's like, oh, what's the order of how you're displaying the names? And then you're just displaying them as they're shown, right? Ford, Mercedes. But it's a little bit difficult for someone to quickly find. If you had like 50 car brands here, how do you find a list with 50 car brands? Instead of just rendering the list as is, you can do car brands dot sort. That's usually a functionality, a method that's already baked into this array here. So you call car brands dot sort, or maybe car brands equals car brands. Again, Python's a little bit weird with this kind of stuff. And then it would sort everything by alphabetical order. And that's one of the beauties of using data structures. So I showed you what array is. We're going to move to hash tables here. So hash tables are pretty useful. Let me show you what a hash table does. Hopefully I can show you guys a good example of it. So I think you could do probably something like car brand names is So you had all these car brand names here. And what you can assign to it is you can assign a value to a key. So this is called a key. This is how you find what you want to look for, which is the value. So when you think of a dictionary, what is this called? They called it a hash table. Yeah, so this is called a dictionary. And I guess in the most basic sense, a dictionary is a phone book or your contacts list on your phone. And whenever you want to look for somebody's number, you would open up your contacts and you would scroll, and then you would find the name of the person that you want to contact, and then the value of it is the number, right? In this case, we're going to do is these car brands American? So is Ford? Yeah, Ford is American. Mercedes is, I think, American also. So once you have this dictionary, you can quickly find the values if you know your key. If, for example, if you had two arrays like this, I'll give you 1 second. 1, 1, 0, 0. Okay, you see how 0 is here, 0 is here, and then Honda. So this array is the same order as this array here, and then it's a different representation of this dictionary. So what I'm doing is I'm just trying to show you why dictionaries are useful. So say I wanted to find if Ford is an American car brand. In this case, in the array case, I will need to find the index of Ford. So I'll need to look at the first index. Is this Ford? No, it's not. Okay, look at the second index. Is this Ford? No, it's not. Okay, look at the third index. Is this Ford? Okay, it's correct. Now let's grab that index, and we'll grab the index from is American, and then we see that it is American. Instead, in this dictionary, what you can do is you can just do is car brand name American, and then you could just do Ford, and then yeah, this is your value right here. You get the point. So if this list was like 5,000 car brands long, you can just find the value that you want by just calling the key. But if you were to find the value from this list here, you need to search up every single one of these numbers, and then it might take you 5,000 operations long. The Ford might be at the last index of this array. So hash maps or dictionaries allow you to call the values of keys that are stored in this data structure very quickly. Okay, stacks and queues are also useful. I would say more so queues. Queues are the way that I've used it in my work is queues. I've used it for if you're running jobs. So if you have things that take a long time on the back end to process, so say you have an AI job that maybe takes 5 minutes, and then on the front end, the user is entering in, let's say, large language query. They're saying, what is the value of, I don't know, my car brands? Is it American? And then say that there's the AI in the back end that needs to do all these processing. It needs to contact a bunch of APIs. Instead of waiting for the response from the back end, you can put this job on this queue, which is in some places like Europe, queues are also used as like lines. So this might make more sense for people who are European, but it's basically you have these jobs that are waiting in a line, and then the one that is in the front, that was, say this job was entered first, this would also be the first one to execute, and then once this is done, then it would start this in the queue, and then this one would be waiting, and then there would be other jobs that are coming in, and then there would be in the waiting state. Okay, hopefully that makes sense. If you do, these operations that you can call are usually baked into this array here. So if you were to pop off like the next value within this list here, you would just run dequeue for Python, or pop. I think pop is for stacks. Linked lists, I don't think you'll need to know linked lists too much, or trees. There's definitely some use cases for trees, but I don't use it too much in the things that I ever had to do. This might be things that you could skip, trees and queues. Yeah, but definitely if you were to go find like a tech job in FANG companies, then they'll expect you to know queues and trees, because they'll do like this coding interview with you. And then some of the test questions that they'll ask you to implement like a queue from scratch or implement a tree. and do like in order tree traversal or something and write it in code. So if you're going for FANG companies, then you need to know everything on here. Okay, but I'm not going to go over it for this tutorial. Data structures. Okay, which is, yeah, this is what I just went over. Okay, on the right side, we have graphs and heaps. So graphs are used not heavily, but it could be useful for some cases. I use graphs to build knowledge graphs. So knowledge graphs are basically, I need to charge my laptop, so I'll be right back. Oh, okay, I'm back. Got my computer charger on. Okay, yeah, I use graphs when I'm trying to build like a knowledge graph. So knowledge graphs are basically, you have something that's called entities and you have relationships. And it's basically, let me give you guys an example. So for one of the things that I need to do for my job, we're building like this chatbot for people to talk to this AI system, and we're building it for the state of Hawaii here. So we have some state officials, they have some like these bill documents that are very long, and then it takes forever for them to read through all of them. And they wanted to see like how like these bills are connected to other bills. So what I do is I'll break down these bills by entities. And the way that I define entities are like anything that can be extracted from those bill documents that refer to like a department, or does it refer to like a committee, like the financial committee? Does it refer to agriculture department? And then I see how these, or I build like this knowledge graph of how these entities are related to each other. So say that there's like bills that talk about fireworks, and then there's certain departments that have jurisdiction over everything that needs to do with combustions or fire, or maybe there's one specifically for fireworks. And then I can see, you can start to visualize how everything is like interconnected. And the reason why I'm doing that is because when you go and query the AI system, because I'm building this chatbot, that when they have a question about fireworks, then the AI can access this knowledge graph to see how everything is interconnected, and then bring in the information that it needs to answer the user's questions correctly. So that is the only time that I'm using graphs. And this website indicates that there's directed graphs and undirected graphs and spanning trees. So directed graphs are basically, they have arrows on it, and an undirected graph doesn't have arrows on it. So a directed graph could be something that maybe one is connected to the other, which can show you the influence one entity has on another entity. Or if something is undirected, which could be a graph showing how two things are just, there's no direction to it. Another way to think about it is in Facebook. When I think in Facebook, the way that they handle the backend is that they'll use graph databases, where I think if I add my friend John as a friend, I send a request to him, and if he doesn't accept it, it just says that I'm following John. Or I guess that's also baked into LinkedIn. You can follow people, but they don't need to follow you back. Also similar to YouTube. So I think a lot of tech companies use graphs quite heavily. I'd say it's pretty simple to learn. You don't need to spend too much time on it. I think if you were to work at those big tech companies anyway, you'd probably want to maybe spend some time looking at what they are. But studying these data structures here are more important. And a heap. So a heap, you can build like a min heap and a max heap. It's a tree data structure where the max value or the min value, depending on which one you're building, it's put to the top. I think these are useful for, let me try to think. It says priority queues here, which I guess it could be useful because say that you have a bunch of jobs that need to be executed, and then those jobs are, you have one backend that's processing all those jobs, and then you set a priority on which one should be executed first. So this queue here, instead of doing like this regular queue where things are processed in order, you can have an extra value on there that moves things that are higher priority to the top. And having a tree-based structure is useful because you can access elements logarithmically. And if you don't know what that is, it's basically, it's faster than doing it one at a time. But I think that brings us to the next step here, which is asymptotic notation. Yeah, so this is a good resource just to look at what complexity is. And I think this is important to know, especially when you're trying to design systems that are very efficient. So basically, like I said before, as you're learning like dictionaries, you can access elements directly. So this is like the cost that it would take in order for you to access the value that you want. And it'll take in order of one constant operation. So this will take one constant operation, whereas something like an array, if you have, say, something that's 50,000 elements long, then it'll take, every time you access each element, it'll grow linearly as the element size grows linearly. This is hard to see when you're actually coding, because most of the things that you work on when you're testing stuff, you're usually working on small data sets. But I guess like in the real world, these data sets can be very long, potentially. You might have like millions of people, like say Facebook or Instagram. They deal with like millions of users a day. So they need to find algorithms or data structures that they can utilize in order to cut that processing down. Say that you had something that's in this red range here, which is indicated as horrible. You usually don't want anything that runs in this red portion here. There's some cases where you can avoid it. So if you have something like a matrix, right? I hope you guys know what a matrix is. If not, can I just search up a matrix? Maybe matrix array, matrix computer science. Okay, yeah, so this is a matrix. So as I was saying, if we have some kind of matrix here, you might not have a choice on what complexity. Basically, if you wanted to run an operation on each one of these values here, say that you wanted to add 1 to each number, then you need to go through each element in this matrix, and there's no way that you could avoid operating on each one of these elements. Say that you had maybe like a GPU. So that's what GPUs are good for. You can do like a batch operation that does all of these calculations at once. And then sometimes these matrices can be like 5 million elements long on the X and 50 or so elements long on the Y. Yeah, so they can be very long, and that's what GPUs are good for. I think that's pretty much it. So here we have some runtimes for the data structures and how you would access the elements. So this is another thing to consider too when you're building something that needs to be optimal, that there's certain functionalities with data structures that have like a better time complexity. So this constant time 1 here is what you want to look for. Sometimes there's certain cases where accessing an element might be long, but searching for an element might be slow. So accessing might be fast, but searching for an element might be slow. Depending on what your use case is and what context you're building in, say that most of the time you're not going to do a lot of searching on the elements. So using an array might be the optimal data structure for you to use, because looking at this, there's nothing in here that has a constant time for searching and accessing, right? You could use these other data structures here where you could have log n and log n. So you would have a best of both cases, and log n is about as good as constant time. Of course, it's not like, it's pretty close to being good as constant time, which this makes it look like it's really good actually. But I think if we zoom in here on these two, there's going to be a discrepancy on what is like the differences between those two. I think showing this graph here and showing these other time complexities, it makes it look like log n is as good as constant time, but it's not. Okay, that looks good. Okay, so that's what I explained here. These are the runtimes. And then you also have space complexity, and that's basically the same thing. As your elements in your list grows linearly, it'll grow linear time. But if you use certain data structures that it adds like a useless property to it, then now you're storing another value to each element, which takes up some space too. This is like the worst time time complexity or space complexity which is big O, and then something that has maybe like the best time complexity that it can have. This would be the best time complex. This would be the slowest. Most of the time you're looking at this big O here. I haven't had a interview, and I've had like over a dozen interviews, maybe 20 even, where all you care about is just this big O. Okay, common algorithms. Okay, so if you're looking for a tech job, then definitely you need to learn every one of these. Because that's what I don't like about interviewing for big tech companies, because the questions that they ask you is pretty random. And then there's so much that you need to know in order for you to pass the exam, the coding interview. It's something like Google. If you're going for like a software engineering job, then they have you go through like 5 different interviews, and hopefully you'll do good in most of them, and then you'll do okay in like the select few. You can work yourself through the problem by maybe designing something that is somewhere as close as optimal. You're headed towards the right direction, and then the interviewer will give you some help. But most of the cases, if you are building something for like a smaller company, maybe just a basic Fortune 500 company that's big tech, then you aren't going to need to know how to build these sorting algorithms from scratch. In Python, you can just call it .sort on it. And in most of the cases nowadays, you just go to Claude or ChatGPT, and then you just say to build an optimal algorithm that sorts this array, or whatever you want to do, depending on where you want to go in life, what kind of tech job that you want to find. Caches are actually pretty important to know. Let me draw another picture for you guys. We'll draw 3 circles here, and then we have this database, and then we have the user, client, and we have this cache. Okay, so if I wanted to access data from this database, say I'm looking up car brands, and this database is in Hawaii, this database is somewhere in the middle of America, I would need to access data all the way to that database, which would take some time, network latency, and then this database it's storing all the data as a list, because they have someone who didn't watch this video and they're storing everything in the list. So it needs to go through the elements one by one. So it'll take some time to find what I'm looking for, and then it'll come back with my answer. And then the next time I try to access something, it'll go through that same network latency, and then it will take some time for it to process, and then it will go through the client. Here we go. So what this cache is doing is, if this is implemented, if I want to fetch some data, it'll check this cache. It'll be like, hey, this is data in the cache. No, it's not. Okay, let's go to the database. We'll grab everything that I'm looking for, but then we'll also grab some other data that might be useful. So then it'll take a little bit more time in order for it to grab that data. It'll come back to this cache, and it'll store what I'm looking for, and also it'll store the other things that it thinks that I might need. Say maybe I'm looking for Toyota brands, and then it sees that I'm looking at Asian car brands. It knows if you build this cache in here, if you build something that's optimal, it'll hopefully grab something that I'm going to be looking at in the future. So then it'll come back with the data that I want. And then since it stored like a bunch of the data within here, then it can just access this cache and it'd be like, hey, you have a cache hit. So let's bring that data back. And then we don't need to go through the database, which it has like all the data stored on there, everything stored in lists, and say this cache is holding just a few select car brands or data that I'm probably going to be accessing, and then it sends that to the client. Okay, so this cache here just speeds everything up. Recursion is pretty confusing. So recursion is when you have a function, say you have a function that, what is it doing? You can pretty much turn like anything into a recursion function. So something that's operating on like a bunch of elements within an array, you can cursively have that function call itself with different parameters, and it's just sometimes it makes the code nicer to look at because it reduces the number of lines, and sometimes it's easier to read. Sometimes it makes the code very confusing to understand, especially when I'm trying to write recursive algorithms. They can be pretty tricky to learn, but if you write the code iteratively, then it's actually, I think it's most of the time it's going to be much faster, because every time you do a function call to the system, function calls takes longer for the system to operate or process whatever logic that it needs to do that you're calling it for. Yeah, and they have tail recursion here and non-tail recursion. I don't know if I need to go over it in this video. I tried to explain what recursion is. It's a little bit too confusing, I think, for what you need to know, but I'd say you probably don't need to learn this. You could just ask ChatGPT or whatever to write a recursive algorithm for you, but it's not going to be optimal anyway, so maybe you don't need to learn it, but all right, make your decision for yourself. Searching. Okay, so searching is, they have two things listed here. If you're trying to find elements that are like within an array that you need to go through one by one, then if that constitutes searching, then I guess there's only two. So binary search is, you have a tree, so binary tree. So since I taught you guys what an array is, where you need to go through each element in an array, then that can be pretty slow, which is when we saw in this asymptotic notation here, we saw that it can be pretty slow. Binary search is actually log n for searching. Binary search tree, yeah, it's gonna be log n. Okay, so this is a good example here. So if I wanted to search for the number 27, it'll go through the top, and instead of searching through each one of these elements, you can see, is 27 greater or equal to 21? It is, so we'll traverse through this side. 27 is lower, and then 27 is greater, and then we found it. So we're cutting the runtime in half every time that we need to find, or that we're traversing down the levels of this tree. So instead of having, how much elements are here? 2, 4, 16, 15. Instead of going through 15 elements, one by one, it goes through 1, 2, 3, the height of the tree. Okay, so binary, or where are we? Binary search is faster than linear search. And then we have these tree traversals, which is also useful for if you want to get into big tech. You need to know these tree traversals. It's pretty easy actually using recursion. The way that I remember it is that where you're calling the function, you basically just want to put the function call above. You're switching the order of where you're putting the function call. So let me give you an example. In order tree traverse Python recursive. Yeah, so in order traversal, you put your print statement here in order for you to print the values of this tree in order. If you wanted to do like pre-order traversal, then you would move this print statement, and all of this is process, but process could also be print. You move it before, and if you have post order, you would just move it after. Okay, breadth first search and depth first search. So these are also useful for graphs, as you see here, depth first search and breadth first search. These are just ways that you can search for elements that are within these graph data structures or trees. Basically, trees are graphs, but it's just ordered differently. Graphs, I think they have a more general kind of data structure that can fit other use cases. Greedy algorithms. So I think the most important one in here is probably just Dijkstra's algorithm. It's also mentioned here. And A-star algorithm, those are usually used for programming video game AI. There's probably better alternatives out there, but from what I learned in school, A-star algorithm is what you would use to program an AI. It's basically used for path finding and how you would program it to find the path to attacking the user or something. Okay, so string search and manipulation. From what I've seen in like tech companies, I think Google likes to use a lot of the string search manipulation, probably because they're dealing a lot with searching and using text. If you were to find a job outside of tech, you don't need to know too much about this. Floating point numbers and floating point math. If you're working with C and C++, then I think this is useful. but I'm going to skip it because I never used it before. Character encodings, bitwise operators. This is also used for like C, C++ if you're dealing with bits. Well, they're also used in cryptography, which I guess I believe that's in like security, computer science, image processing, and other applications. I never used this, so I'd probably say skip. Character encodings. Yeah, this is useful for knowing how characters are represented if you're building like a web application. And because I think there's certain formats of like files where you need to know how things are like converted to ASCII or Unicode. I think this is also used for a lot of times in networking. So if you're going into a job for networking, then I think this is more useful. But for building web applications, I'd say it's slightly useful. Common UML diagrams. So everything in tech and web design, it's with diagrams. I think UML diagrams are these. So yeah, I don't know if these are actually used in industry too much. For the things that I have to do for my work, it seems a little bit too structured. Most of the time, if you're working with other computer scientists, and then nowadays people are just using, this makes it look like computer science is pretty scary because this interface looks bad in my opinion. Getting the high level idea of how to represent your architecture or things that you're building in your system at a high level so you can communicate your design or how you're building certain things in a certain way to other software developers, then just design your diagrams in the easiest way to understand. So if you were to describe it to your drunk grandma, just describe it or build it a very easy way to understand. And I also get this from learning more about marketing. If you can describe your application to people who are smart, who know software engineering, then it'll help them. But there's other people who are like maybe new to computer science. You're not taking away information from dumbing it down. You're just making it even easier for those other smart people who know software engineering to understand whatever you're trying to say even more. You're just attracting a wider range of people to understand what it is you're trying to teach them or what you're showing them. And then design patterns. This is something that I'm still studying myself. This is probably what I would learn more deeply about, which is like how you're designing your actual web application. But these other design patterns, they sound interesting. I haven't heard of them in my software engineering classes, but maybe I'll check them out after I finish this video. But I don't know too much about these, so maybe I wouldn't pay too much attention on it. Basic math skills. So yeah, you need to know like your basic math, adding, multiplying numbers together. I think if you're going more so in like a data science kind of job or role, then you need to know more of like conditional probability. Maybe you're going in like a research lab and you need to do some math, but most oftentimes I don't think you're going to be dealing with math too much in software engineering. Yeah, I wouldn't focus too much on it. Complexity classes. So there's this thing in computer science where there's certain problems that are like there's no optimal solution for it. You can get like a best guess of at most times, but you can't prove that the algorithm that you built is or is not optimal. And the only reason why you would need to know this is if you had a boss who's saying, why is this application slow? I want you to optimize it and make it as fast as you can. There's ways that you can prove that there is no optimal solution, but you can't build it. And then they have some examples here of NP complete problems, which are very popular, especially if you're trying to find a FANG tech job, then they'll probably ask you questions about these. But in practice, in an application setting, the only reason you need to know this is if your boss asks you that question of trying to optimize this. Tries. So tries is another data structure. I haven't used tries too much. I think it would probably be used in like a Google Tech interview, but I would say in practice you wouldn't need to know about it. Balanced search trees, I wouldn't spend too much time on it. And then this network databases and system design is like this is what I know more about. I probably do a separate video on these three things here, which might be my next video. I don't have time. I don't think this YouTube video will have time for me to cover all of these things in here. But definitely a tech job would be a lot easier for you if you were to just focus on these three. I think. Okay, security. Security is definitely important. I've at some point in my life I did find security in computer science useful, more so in the case because I wanted to find a job in security computer science. But I don't know too much about it. But if that's something that you are trying to get a job for, then yeah, definitely find or click on this and learn more about it. How computers work. Okay, so this is one of the reasons why I think like the things that you learn in school, they'll teach you everything that they think that you need to know. Like how does a network work? How does a router work? How does switches work? What are all the internal components of a computer and how data is passed through? But I think at a high level, you just need to know what a RAM is, what a RAM does, what a CPU does, what a cache does, how your computer is running a process, and how processes are different in threads. But I don't think you need to know too deep on how everything works internally. It's interesting to know, but in a practical use case, I don't think it's like the things that they teach you in universities, it might be like too much into the weeds of how all these internal processes work, which aren't going to be used like in practice. But if you're making a decision on running on like an AI model that needs this CPU and this much GPU, and if you have a question on we have this much data and we want to build this model, what is the best components of a computer that I need to have in order to run that model on, then those are like probably the majority of questions that you'll have on needing to know how a computer works. Okay, and then I think that's mostly it. We have a few things here that I have never heard, so I probably just say skip those and let me just take a quick look. Yeah, I've never heard of these before in my life, but in practice, I don't think those are going to be too relevant on what you need to learn. And that's it for the computer science section of the roadmap. Thank you all for sticking around to the end of the video. Again, if you guys like this series and you guys want me to continue going through every one of these topics here, then give this video a like, subscribe if you want to see more of this series. I have a computer science PhD degree, so if you have any questions on things that you want me to go over or anything like that, feel free to ask me. Write down a comment down below on this video, and yeah, thanks for watching.